Hello everyone and welcome to yet another video about math. In this video I'm going to go over some topics dealing with quadratics, and the first thing that I'll do is go over some characteristics of quadratic functions. We'll do standard versus vertex form and how to tell those characteristics from standard and vertex form. Then we'll go over into some function transformations, and finally we will look at an application, maybe two at the end of the video. Let's get into it. On this first slide, I'm going to go over the characteristics of quadratic functions, and you can see here that we have two different graphs. We have this is a quadratic function. This is the graph of a quadratic function, and on this one over here, this is also the graph of a quadratic function. We call these graphs parabolas, so I'll write that down over here. And these parabolas have characteristics, as you can see here in the middle. So the characteristics that we are going to be most interested are all highlighted here. We have x int, which is shorthand for intercepts or intercept. X-intercept is where the graph crosses the x-axis, and you can see that we have a couple of x-intercepts on this left graph over here, and we have one x-intercept on this graph over here. It is something that I should note here really quick. We could have a quadratic function that looks like this. And the example here, this quadratic function would have no x-intercepts. Moving on, we have y-intercept. So we have the x-axis, y-axis. If the x-intercept is where the graph crosses the x-axis, well, the y-intercept is where the graph crosses the y-axis. So here we have the y-axis, the blue arrow pointing with the blue text here. The y-axis or the y-intercept for this graph would be here. The y-intercept for this graph would be the same as the x-intercept. Okay, that happens sometimes. The next bit of information we have here is the vertex. That is the center point of the parabola. So the center point of the parabola is up here. It's a little bit hidden. Let me darken that dot. There we go. So this is the vertex up here. You can tell, again, green text, green arrow, all right. And the vertex over here, again, is going to be this point right here. Now, another way to know that this is the vertex is to notice that this is either the maximum or the minimum of this graph. Now, maximum or minimum refers to a y value. So this right here refers to a y value. And it'll either be the biggest y value, which we would call the maximum, or it'll be the smallest y value, and that's what we would call the minimum. So another way to think of that is you have a maximum if the graph opens down. So when we say opening down, you can see that the arrow to the left and the arrow to the right are pointing down. This graph is opening down. And we would say that it has a minimum if the graph opens up, like this one over here, arrows pointing upward. So this would be a vertex that represents a minimum. On the left graph over here, this would be a vertex that represents the maximum. But max and min are just descriptors for the vertex. Next, we have the axis of symmetry. This is a line that divides the parabola in half. You can see the axis of symmetry is here for this one, and the axis of symmetry is here for this one. And then, of course, we can find the domain and the range of these graphs over here. So the domain is super simple. It is all real numbers, or negative infinity to infinity if you're using interval notation, and the range changes just slightly. And I have this weird notation here with k to infinity as an interval. If it's opening up, if it's opening down, the range will be negative infinity to k. And k, and you'll see this in a couple slides, k is just the y value of the vertex. All right, so The k value here would be 9, and the k value here would be 0. So what I want to do now is just go through and label these really quickly here. So the x-intercept technically should be written out as ordered pairs. So when we look at the x-intercepts on this graph, we can see that the graph crosses at the x value -7, which would give us an ordered pair of -7, 0. This x-intercept, the graph crosses this x-axis here at -1, which would give us a second x-intercept at -1, 0. Now sometimes you might just be asked for the x values, so you may have to report answers that are just -7 and -1. Something similar going on with the y-intercept now. So the y-intercept is where the graph crosses the y-axis, which is way down here at -7. And if you want the coordinates of this point, your x value would be 0. 0 because we don't move left or right any amount, and we go down 7. So -7 would be the y value for the y-intercept. So this would be 0, -7. All right. The vertex, as I mentioned earlier over here, the vertex, this is either the maximum or the minimum point, which is way up here. Again, it's the center point of the parabola. And so this is the vertex here. We just have to find the coordinates of this point. The x-coordinate is -4. The y-coordinate is 9. So the vertex here would be -4 and 9. Next, we have the axis of symmetry. So the axis of symmetry is the equation. It's an equation of a line, but it's a line that divides the parabola in half, and I abbreviate axis of symmetry. In most cases, the vertical lines will be x equals some number, and again, it's real easy to see what that number is. If you just follow this line down to the x-axis, it'll be x equals -4. And that vertical line just means the parabola, more than it divides a parabola in half, it is symmetric around this line. So if I go all the way down here to this point, if I go left to get to this point, it would be 4 units. To get to the same point going to the right, it would also take 4 units. And that works with any pair of points you see plotted here. Left one, right one. Boom. They're symmetric about the axis of symmetry. Now lastly, we have the domain and range. So the domain here, no problem. You can just write the all real numbers, that's fine. And this parabola is in fact opening down. So since it's opening down, our range here, R for range would be -infinity to the y value of the vertex, which would be 9. So here is the range. In fact, I'm going to give you a chance to figure out all of these characteristics for this function. And I have one more on the next page for you to try as well. So go ahead, pause the video, try this one. So here are the answers, and before I go over these answers, I want to address, I did make an error here with the ranges. We do not use parentheses around the actual number. As you can see, I fixed it here. So for all of these other ones, you want to go back and change these to square brackets, because we do get to include the y value for the range. So here goes all the information for this particular parabola. The x-intercept, where this graph touches the x-axis, the x-coordinate is 0. And again, the y-coordinate for any x-intercept is always going to be 0. The y-intercept here is where this graph crosses the y-axis, which is right here, y value 0. The x-coordinate for any y-intercept will be 0, just like this over here. The vertex here, my goodness, it's all 0, 0. So the vertex here is 0, 0. And this is a minimum. And I'm actually going to write this here. This is a minimum. This one was a maximum. The axis of symmetry here, we have a vertical line that is going vertically through the vertex. You may have noticed that it happens over here. If the vertex is the center point of the parabola and the axis of symmetry divides the parabola in half, the vertex has to be on that vertical line. Okay, so here is the axis of symmetry. What's the x value that this line goes through? Well, it's 0. The domain, negative infinity to infinity, just to show you that either one of these notations is fine. And since this parabola is opening up, we will have a range of 0 with a square bracket around the number to infinity. Okay, I have one more example for you to try on the next page. So in about 5 seconds, I'll go to the next slide and you'll have about 10 seconds to pause the video. All right, here are the answers for this particular example for all of the characteristics. We have the x-intercepts here and here for our parabola at 0, 0, and 4, 0. And again, I want to point out the y-coordinates are 0 for any x-intercept. The y-intercept here, I'm going to have to use an arrow, is right there. And the y-intercept is 0, 0. That's where the graph crosses the y-axis when the y value is 0. So again, for any y-intercept, the x-coordinate is 0. So I want to point out if one of your intercepts is 0, 0, it will also be the other letter intercept as well. So if your x-intercept is 0, 0, guess what? The y-intercept is also automatically 0, 0. If the y-intercept is 0, 0, then the x-intercept is automatically 0, 0. All right, so we have a vertex here. The vertex is way down here, and it is a minimum because this graph is opening upward. But the vertex here is 2, negative 4. We have an axis of symmetry here, which is x equals 2, and that is a vertical line going through the parabola here, and you can see that the axis of symmetry is in fact lined up with the vertex. All right, the domain, again, all real numbers, just write it down, don't think about it. But the range, since it's opening up, we just take the y coordinate of this vertex right here and use it. The y coordinate of the vertex will always show up in the range for a parabola. Just like, maybe you noticed this, the x coordinate of the vertex is the value used in the axis of symmetry. All right, so as promised, I'm going to get to what exactly that k value is on the next slide. So the whole point on this slide is to talk about vertex form, and I will get into standard form on the next slide, and the differences between them and how to convert from standard form to vertex form, again on the next slide. But then after that, we want to be able to tell what are the x and y intercepts, what's the vertex, what's the range, what all that stuff that we were doing from a graph. I want to be able to figure all that out without looking at a graph. And it is just generally easier to do when you have a quadratic equation in vertex form. So we start out with vertex form. And you can see that I've written down a more generalized idea of what the vertex form is over here. So f of x equals a times the quantity x minus h squared plus k. Here's the k I was mentioning earlier. So why is vertex form awesome? So vertex form is awesome because it tells you what the vertex is. Right here I have this value and I have this value. H and k. So how can you find the vertex? Well, the vertex is just the ordered pair h comma k. And really what you have to keep in mind here is that when you have a quadratic equation in vertex form, you can't just copy the number that's here. Like I cannot just write 4 as the x-coordinate of the vertex. What you have to do is you have to take this entire expression, x minus h, whatever's in the parentheses, you have to set it equal to 0 and solve for x. So plus h, and it really ends up being that most students understand that it is the opposite of the number in the parentheses that ends up being the x-coordinate of the vertex. And I'll show you again when we get over here. So the vertex is h comma k. Very easy to figure out. That's why we call it the vertex form. So now, second thing that we have to do is, I think the second easiest thing that we can do here is find the domain and range. So the domain here, again, negative infinity to infinity, or you can use the r, the double bar r. But the range, again, will be either k, this time with the correct symbols around it, either k to infinity or negative infinity to k, just like you learned in a couple slides ago. But now we don't have a graph to tell if it's opening up or down. But remember that it'll be k to infinity if the graph is opening up, or negative infinity to k if the graph is opening down. And again, we don't have a graph. So how can we tell if this function represents a graph that is opening up or down? Well, that's not too bad. All we have to do is look at the a value. This value right here. Whatever number is in front of the set of parentheses, fine. So if a is positive, then we know the range will look like this. But if the a is negative, then the range will look like negative infinity to k. Negative, there we go. So we have to include the a value when we figure the range. Next, x and y intercepts. So the y-intercept, I think, might be the next easiest thing to find, is you find f of 0, and that gives you the y-intercept. And the x-intercept is so much more involved, but the x-intercept you find by setting f of x equal to 0, and you solve for x. And that's it. So here we have all of this stuff for the vertex form of the quadratic. So to start out real quick, and I'm not going to do the axis of symmetry here. That's easier done on a graph. Again, you could just write, if you wanted to, you could just write x equals h, and you're good to go with the axis of symmetry. Okay, so the vertex here for this particular example would be, so I have it in blue now to match up with the vertex over here. The vertex would be negative 4, 8, because if you take what's inside this set of parentheses, x plus 4, you set it equal to 0 and solve for x, you would get the negative 4. That's here. The y-coordinate of the vertex, again, is just this value that's either being added or subtracted. So the domain and range, pretty simple. Domain, all real numbers. The range, okay, so we have to do a little bit of work here. I know there's going to be this number in the range. It's got to be 8. 8 has to be there, so I'm just going to write it here to see what happens. Let's see. we have to look at the a value. The a value is -2. Okay, it's negative, so okay, this is what the range will look like right here. It'll be -infinity to 8. Awesome. Next, the y-intercept will be the easiest thing to find next. So that is to find f of 0. Well, in this case, our function is called m, but we still put 0 in for x. So we're going to find m of 0, which means all we have to do is substitute the x out for 0 here, squared plus 8. There we go. So what do we do from there? Oh, I guess we just have to simplify this, huh? So let's see. Order of operations. 0 plus 4 is 4. 4 squared is 16. So I'm going to rewrite this. This would be -2 times 16 plus 8. So -2 times 16, now we do the multiplication. -2 times 16 is -32. Then we can add the 8 to that to get -24. So again, for the y-intercept here, the x-coordinate will always be 0, and you can plainly see that because we substituted x out for 0. The x value is 0. And the resulting value we get, this -24, will be the y part of the y-intercept. Hooray! Finally, the last thing that we have to do is find the x-intercepts. Now the x-intercepts, again, are a little more involved. So what we have to do is we have to take the function f of x and set it equal to 0. But I don't want to write m of x equals 0 because then I can't solve for anything. What I want to do instead is I want to write this side of the function equal to 0. So here we go. The x-intercept, or intercepts, right? We could have more than one. In fact, we can have up to 2 of them. The x-intercepts, we would have to write 0 equals -2 x plus 4 squared plus 8. So how do you solve this thing for x? Well, the first thing we have to do, or our first goal really, is to isolate this piece of the function. We want to isolate the set of parentheses that are being squared. So that involves a couple steps here. We have to move the constant that's either being added or subtracted. So I would subtract 8 from both sides. And you would get this as a result here. -8 equals -2 times x plus 4 squared. Notice we still have not isolated this piece yet. That's because we have this -2 being multiplied in front, so we would have to divide both sides by -2 to reduce that away. And we're doing all of this so that we can eventually take the square root of both sides. So now we have 4 equals x plus 4, the whole thing squared. We'd say x plus 4, the quantity squared. Now, since we're trying to solve for this x, and it's trapped in this set of parentheses being squared, we have to get rid of the square now. So getting rid of the square would look something like this. We have to take the square root of both sides. The side with the number on it, we would have to throw a plus or minus in front of it. So here we would have plus or minus 2 equals x plus 4. And then finally, the last step here would be to subtract 4. Now this is an odd thing. We cannot immediately subtract a 4 from this plus or minus 2. We just have to write it in front and do a little figuring. So I'm going to do a little switcheroo as well. So these are reduced away to 0. So I would have x equals -4 plus or minus 2. So what does this represent? Well, first, we would have to take this -4 and add 2 to it. So -4 plus 2, I'm going to represent this like this, plus -4 plus 2 is -2. And then we would have to go back through and take this -4 and subtract 2 from it. So we're going to add and subtract the same number, but not at the same time. We have to do it separately. So we add once, we subtract the other time, and get a negative 6. So what happens then is we have two x-intercepts. Here, this one would tell us negative 2, 0, because the y-coordinate has to be equal to 0 for an x-intercept. And this one would tell us negative 6, 0 for the x-intercept. So that's a lot of information to take in, and you get one good example on vertex form, because when we look at standard form, it'll be almost the same thing. Our first step will be to turn standard form into vertex form. Let's take a look. Well, this looks totally different. Yes, it sure does, but it's only different in looks. So our goal here is to turn this, which I'm going to say is in standard form. It has 3 terms, or all separate terms. We don't have a binomial being squared like in vertex form. We want to turn this standard form quadratic polynomial into a vertex form quadratic. Because if we can turn this into this form, then we can just use the process that was done on the last page. So how can we do that? Well, there's this little, it's not going to be immediately obvious, this little way we can find the x-coordinate of the vertex. And it is this little formula here, x equals negative b over 2a. Now, if you know anything about the quadratic formula, you know that negative b is the beginning part of the numerator, and it's all over 2a. So that might be a way for you to remember this. So how do we find b and a? Well, if we just come over here and write our standard form general equation here underneath our standard form specific equation here, bx plus c, we can find a is 5 and b is negative 30. And yes, you must include the signs that go with these numbers. If it's a positive number, then of course you make it positive, like this one here. If it's a negative number, well, then you have to make sure b is loaded up in this formula as a negative 30. So here we go. This will be negative b, which is going to be negative 30 over 2 times a, which is 5. Let's see, negative 30 and 5. There we go. So what do we get? We get 30 over 10, which is 3. So this is the x-coordinate of the vertex. Yay, we did it. That's great, but that's only half of it. I hear you all asking out there, that's only half of it? How do we find the other half? Well, we just have to remember that the y-coordinate is what you get when you put the x-coordinate into a function. So I used f here because that's generally the name we use. So we have to just take the x-coordinate and put it back into the function, which in this case is called g. I understand it's a different name, but we would just have to find g of 3, which means I replace all of the x's with a 3. 30 times 3 plus 25. And when you number crunch all this out in a calculator, you'll get negative 20. So great, we know the vertex then is 3, negative 20. So in the vertex form of our equation, we would have f of x equals, or I guess this would still be g of x because we're transforming g of x. So g of x equals x. I know there's an x in there squared. Fine. So remember, when we had a vertex, we would just get the y-coordinate from this number out here. So I can just write minus 20 out here. That's no problem. But the x-coordinate is a little tricky. It's a little slippery. It's going to be the opposite. Remember, if we take what is inside this set of parentheses, set it equal to 0 and solve for x, we should get this, which I already mentioned as well, that students normally just remember that it ends up being the opposite of the number grouped up with x. So that works in reverse too. We have to take the opposite of this number to put it into the equation. Now you'll notice here we have f of x equals a x minus h squared plus k. So I have h, I have k. What is a? Well, it turns out a in vertex form is the exact same number as a in standard form. So a that we started with is 5. The a over here will also be 5, which is nice. And there we have it. We have it in vertex form. So now what you're going to do is you're going to go through. We already know what the vertex is, right? The whole goal here is to find all of those characteristics we found on the previous slide. The vertex, so you're going to go through and find the domain. You're going to find the range. Here, let me help you out. Whoop, negative infinity to infinity. Don't think about it, just write it. The range, that'll be a little bit different. Remember, you have to use the a value in this case. Then you'll want to find the y-intercept. And then finally, you'll want to find the x-intercept. And the x-intercept solving process will be exactly the same as the last slide. So I'm going to stop talking, pause the video, see if you can get it. I'll come back in about 10 seconds with the answer. All right, here's everything. The domain, I went over that just a few seconds ago, no problem. The range, so we have to find the range based on a. A is positive, which means the graph is opening up, which means negative 20 will be a minimum value. Remember, k, the y-coordinate of the vertex, will always show up in the range. So since it's a minimum value, the y values will get bigger from there. The y-intercept, again, you'll substitute 0 in for x here. You'll get 0 minus 3 is negative 3. Negative 3 squared is 9. 5 times 9 is 45. 45 minus 20 is 25. Or you can just literally use a calculator to crunch that out. So the x-coordinate was 0. The y-coordinate was 25. Just like I've been saying, whenever you substitute an x value into a function, you'll get a y value as your answer. Okay, it's the y value. Lastly, the x-intercept, if you substitute, if you set the function here equal to 0, check, move the constant term to the right, check, that's adding 20. Then getting rid of the number that's multiplied, aka the constant multiplier that's there, if there is one there. It could be 1. If you want to divide by 1, that's fine. So here we have 5. We divide by 5 and get 4. So we would have x minus 3 squared equals 4, as you can see here in the black ink. The red ink tells you the next step. We would have to take the square root to get rid of the square here. We'd have to take the square root of the other side as well, with a plus or minus in front of that constant. That would leave you with the square gone as x minus 3 equals, the square root of 4 is 2, again, so we'd have a plus or minus 2. This number could change. It could be 9, it could be 16, it can be any, normally it's going to be a positive number. Anyway, so square root of 4 is 2, plus or minus 2 is there. To solve for x here, add 3. Again, just shove that number in front of the plus or minus so you get x equals plus or minus 2. You have to go through and add these two. 3 plus 2 is 5. You have to go through and subtract these two. 3 minus 2 is 1. Pair those up. Pair those x coordinates up with the y coordinate 0. All done. So here are the x-intercepts. And if you really, really are curious and want to know, the axis of symmetry here would be x equals 3. Let's keep learning. On this slide, we are going to go through and figure out the equations of these graphs. You may have noticed that this graph here and this graph here are very familiar, all the way back from the first graphs you saw in this whole video. But what we need in order to make these graphs, or make equations out of these graphs, is first we're going to assume that a either equals 1 or a equals -1. And this has a lot to do with what I said when we were finding the range of these last couple examples, one in vertex form, one in standard form. Positive A means the graph opens up, and negative A means the graph opens down. So that's going to help us in our formulation of these equations. So the equations here, and we're looking for vertex form, are pretty much going to be solely based on vertex form. So as long as we can find the vertex, I don't know if you remember, the vertex here was -4, 9, and the vertex here was 0, 0, then we can find the equation of these parabolas. So the first one here, I'm going to call this, let's just call it f of x. I've been using f enough. Let's just call it f of x. F of x. All right, first thing, super simple. Is it opening up or down? I mean, this one over here is opening down. So my a value will be -1. We will have our parentheses because we're using vertex form. I will have x here, and the numbers that I will be using are way up here, -4 and 9. So the x value, again, will be the opposite. Let me get my pen. There we go, +4. And the y value gets added or subtracted outside of the set of parentheses, just normally, 9. So it's just +9. There we go. Now, one thing that you can do to clean this up is that a -1 times anything just represents a negative. So we have f of x would be -x + 4 squared + 9. And this is the equation of this parabola. Sweet. Now, for the other parabola over here, I am going to set up another equation. Let's call this one p of x. Why not? So here, p of x would be equal to, since we're using vertex form, we just have to know if it's opening up or down. So since it's opening up, the arrow's again pointing up, we will assume that a is 1. X squared, okay. Again, we have to put some numbers in here. So the numbers that we're going to use, we're going to get from the vertex. So here I'm going to have a +0 for the x coordinate and a +0 for the y coordinate. And from here, we can simplify this down a ton, an absolute ton. So let's say x + 0. Well, adding 0 to something doesn't change it. So this is just going to be x. So this here in the parentheses will be x squared. And in fact, we don't even need the parentheses at that point. So this is going to look something like this now. Let's say p of x equals 1x squared + 0, which is this one out here. All right. So 1 times anything is that anything. So this is x squared +0, and I just went over here. Adding 0 to anything doesn't matter, so this is really just x squared. Wow, all right. So I did this simplification to point out that putting zeros into a vertex form equation doesn't make any sense. X will be squared because it has to be squared because this is a quadratic function. And multiplying by 1, we don't even need to have that. Like, we didn't need the 1 over here. We just needed the negative from that 1. So that's a little odd. This equation is just p of x equals x squared. This is what we call the parent function. The parent function is centered, if you will, at 0, 0, the origin where the x and y axis cross. But this one, on the other hand, holy moly, it has been moved away. It's been flipped over, right? It's normally opening up. It's opening down. We would say this is transformed. This is a transformed function. And you can pretty easily tell how it was transformed. If you can find the coordinates of the vertex, then you can tell me how this graph was transformed. This graph was transformed because the vertex is -4, +9. The coordinates are -4x, +9y. So what this vertex form graph is telling me is that this this was, what do we say, shifted left 4 units. That's what that tells me. And we do left because of this whole opposite thing that's going on, and that's fine. This one here, this 9, tells me how far up or down the graph shifted. If it's positive, guess what? It shifts up. Shifted up 9 units. If this were negative, I would have said shifted down 9 units. Just like if this number inside with x were negative, I would say shifted to the right. The last thing that we have going on here is this negative. This negative is, this negative causes a reflection. A reflection, we can say about or over the x-axis, reflected over the x-axis, reflected about the x-axis. There's a lot of different ways we can say it. But if it's negative, then we would say reflected over the x-axis. All right, one final thing on this slide is that we have here this f of x function that is here could be written a slightly different way to try to trip you up, but don't let it do that. I could write this as f of x equals 9 minus x plus 4, the quantity squared. And you can see how this might trip some people up. But you're not going to let that happen to you because you're seeing it now. You're going to understand it here in a few seconds. The negative tells you the sign of this term. The positive tells you the sign of this term. Now in this equation, there are only 2 terms. And I'll define this for you. A term starts with a plus sign or a minus sign that is not in a set of grouping symbols. So like this plus sign right here doesn't count. So as we move our way left to right, I see a minus, all of this stuff until I come to the next plus or minus sign that is not in a set of grouping symbols. Boom. So this whole thing, negative x plus 4 squared, that is one term. And positive, new term, 9. There's my second term. I can move terms around in an algebraic expression in any order I like. And you can too. So you can see here with this positive 9, right? It's not listed, but we know it's plus. Plus 9 minus, new term. This term had a negative in front of it. Yep, this term still has a negative in front of it. So if you're given an equation that looks like this, you can rewrite it so that that constant term is behind and probably a little easier to see and understand how the transformations work. Now that I've breached the topic of transformations, let's take a look at that on the next slide a little more in depth. On this final slide for the video, thank you for sticking with me. I will describe transformations of quadratic functions. In fact, I'm going to skip over 1. We're going to do 2 and 3 together, and then I'm going to have you try 1 for yourself. So, in fact, we're going to start with 3. So I have this function here, m of theta. Theta is just another variable. It's like a little O or a circle or a 0 with a horizontal line going through it. So this is our variable. M of theta is theta minus 4, the quantity squared. And I want to describe the transformations. Well, basically, I'm just trying to find the vertex and whether or not the graph was reflected. Remember, it's only reflected over the x-axis if we have a negative in front of what's being squared. So this one here, no negative in front, so we know it's not going to be reflected. Okay, pretty easy. Now the only thing we have to do is find the vertex. So if we can find the vertex, It's got to be pretty simple here. We can have theta minus 4. We can set that equal to 0, solve for theta. That means theta would be equal to 4. The y-coordinate is just hanging out here in the back. Well, wait a minute. Where is it? There isn't one. That would be plus 0. If there's no constant being added or subtracted, then we have a 0. It's a 0. So we have an x-coordinate of 4 and a y-coordinate of 0. And I want you to try to picture what that would look like in your head. 4, 0. Where would that vertex be? It would have shifted to the right 4 units, right? It is the exact opposite of what you would think would be happening because you see a negative 4 here. Well, it's not a negative 4 because we have to solve for this value. It's a positive 4. So this means the graph would have moved right 4 units, or shifted right 4 units. Okay, so that's not too bad. And that was the only transformation. There was no reflection, and since the y-coordinate of the vertex was 0, the parabola for this particular graph would not have shifted up at all. So let's give an idea of what we're looking at here. So here, this is what the normal parabola would look like. Come down here, go to 0, 0, come back up, fine. What this graph did, and I'm going to do this in red, is it would shifted 4 to the right. So it would look something like this. There we go. Pretend it's perfect. The next example I'm going to do is number 2 up here. Number 2 is reflected. I can see that. The sign in front of what's being squared is negative. So I'm going to write that down. This was reflected. Oops, I want to do this in a different color. Let's use blue. Reflected. We'll say over x-axis. And what would be the vertex here? Well, I know that I would be able to find the horizontal movement, or we could say the x-coordinate of the vertex, if there were a set of parentheses. But like in the last slide, we had a 0 originally in the parentheses that were being squared, but we got rid of it because it didn't need to be there. So if you have no number in a set of parentheses with your variable, the x-coordinate of the vertex is 0. So this would be 0. And you can clearly see that this plus 15 is not in a set of parentheses with x being squared or the variable being squared. So that has to be the y movement. So the y-coordinate of the vertex would be 15. So our transformations here would be reflected over the x-axis. Yep, there's one of them. And then shifted up 15 units. And I realize I did not use the word shifted down here with this one. But when I say right 4 units, I inherently mean shifted right 4 units. So what would this one look like? This one would look similar to something like this. It would have gone up 15 units, and it would be opening the opposite direction. So it'd be looking something like this. There we go. But there was no horizontal movement from here. It's just the vertex got shifted straight up, and it was reflected to open down. Just like this one, the vertex shifted straight right, and that was it. It just keeps opening up. So for the last example, I lie, we're going to do all these together. The last example here at the top, number 1, we have q of t equals negative t plus 2 squared minus 1. So I'm not even going to find the vertex for this one. I'm just going to think this one out here real quick. Okay. I know it's going to be reflected over the x-axis. What else do we have going on? Well, I know a plus, oh, I've seen that before, not in this one, but if a negative inside moves it right, then a positive inside, the exact opposite of a negative, should move it the opposite direction. So let's say this shifted left 2 units. Now let's see, I do have a number that is outside. It's not being grouped up with the variable like this one. This was a plus 15, which means it shifted up 15 units. That means a minus, again, the exact opposite of a plus, would move it in the opposite direction. So instead of going up, if we have a negative number outside, this would shift down. Shifted down 1 unit. Oops, there we go. So these are the transformations that were done to get this equation, or this function. And lastly over here, I have a function called beta of x, and again, beta is just another name for a function. So don't let that fool you or confuse you. But it's in standard form. So guess what? You have to put it in vertex form, and then you can find the transformations. Go ahead, pause the video, give it a shot. I'll be back in about 5 seconds with the answer. Okay, so here's all the work that goes along with this. We have, in standard form, so we have to find A and B to find the x coordinate of the vertex, which would be 8 in this case. So the a value here ends up actually being -1. There has to be a number in front of it. It's not going to be 0. -1 was a, so you can see for a down here I substituted -1 in. And the b value here is +16. So negative b was replaced with 16. We end up with -16 over -2, which is 8. What do you do with that 8? Well, we have to go substituting it into the original function again. So we substitute 8 back into the function, which means we replace all these x's up here with 8. And again, you can use a calculator or your brain or whatever best suits you, and get 59 for the y value. So the vertex is 8 and 59. And the a value again is -1. Now we don't have to write the equation. You can write the equation if you want to, but this tells me right away that I moved 8 to the right, up 59, and was reflected over the x-axis. And what's really cool is that you could have seen right from the very beginning that you were going to be reflected over the x-axis, because this a value matches up exactly with the a value that we would have written in vertex form. I very much hope this video helps you out, was descriptive enough in helping you learn about quadratic characteristics and how they're transformed and how to get equations and all these other things. Good luck, everybody.